Okay. Good evening, everybody. Uh, this is our fourth interactive session. My name is Saida Said. I'm a PMRF scholar at IIT Roorkee, and we have been talking about what you have studied in the earlier weeks. So, as mentioned in the last class, this week we will be studying about compaction, and if the time permits, we will study effective stress, concept, not exactly study, but we will solve some questions based on these topics. So let us start. Okay, so first of all, let's get a general, let's discuss some general facts about compaction before we can start solving some questions on that. Compaction is a relatively simple topic. All you need to know is that when you have some loose soil in field and you want to do some construction over it, you want to build a building over it, this loose soil will not will settle down as you put load on it because it is not in its optimal uh, configuration, we can say. So what we try to do in compaction is we try to put load on this by the means of rollers. We make multiple passes of these rollers over this soil such so that the air voids. It's very important to know that compaction of soil takes place due to escape of air from the voids and not water. When water is escaping from the voids, it is most likely due to a consolidation process. So if I have a soil matrix that is loosely packed and I compact it, I will have a densely packed matrix. So what will happen is that the unit weight is the weight of a unit volume. So in this unit volume, you can see you have lesser amount of solid material. Here you have and more voids. Here you have lesser voids. So the unit weight gamma dry here, because we're talking about the dry state of the soil. Gamma dry here will increase as the compaction proceeds. So what we want to do is we want to increase the gamma dry of the soil by compaction. Now compaction, uh, how the compaction takes place, there are a few theories about it. With relative to moisture content. See, moisture content technically cannot be zero because there is always some residual moisture left in the soil, even if it is in the driest state. It will have a um, attached or bound water in the uh, around the soil particles. So what moisture does is that when you have two particles and you try to compress them in a total dry state, you will see frictional resistance here. What moisture does is, one of the theory states that what moisture does is it lubricates this such that the particles can move and can form a better packing position. This is kind of a lubricant, it reduces resistance. But only to a certain extent does this water content help in increasing the compaction, because after some time more and more water will mean that more and more voids are present, isn't it? So when the voids water starts replacing the solid particles here from the unit weight, then the unit weight will again decrease. That is why when you draw the compaction curve, gamma d versus w, you see that with increasing water content, the gamma d increases up to a certain point and then it decreases again. So, what are our objectives when we study compaction? Okay. So, what are our objectives when we try to study compaction? Number first is we want to know what is the maximum dry density of a soil sample. So for this, for example, this is a plot of land and you want to construct a house on it. What you do is you take some sample, take it to the lab and do a Proctor test on it. Proctor test will tell you a characteristic property of this soil. What it will tell you is that what is the maximum density to which you can compact this soil. The soil may not be, this soil may have a gamma of 15, and when you do the test, you perform this test and you find out that this soil has a tendency that it can be at maximum it can have a of gamma d of 18, for example. So why is this important? Because now you know how much effort you should put by rolling on this soil. You roll this soil and roll this soil until you get this density, because this is the best density that you can do. Other thing is the optimum moisture content. Again, from Proctor test you calculate at what moisture content does this soil get its highest density. So you sprinkle water on field, you try to get this soil to this optimum moisture content, then you roll for the best results. So this is how you translate what you found in the lab to the field. What is the requirement of this test is that it will tell you that the soil that you have, how much compaction it needs and how much compactive effort you should give it. So you can decide the number of passes of rollers, the uh, height of layers in which you should pass the rollers and everything. So this is for preparation of the land before construction. So that was the second important question. First important question was what is compaction. Second important question was what uh, are the determinants of compaction, that is MDD and OMC. And the third thing is what is the structure of soil when it is compacted. So if you have a soil, as you compact this soil from this density, this water content, this density to this density, and then again you have this low density. What is the difference between this soil and this soil? Even though both of them have same density, but these soils are not similar. How, like, this you should know, because this type of soil is has different applications, and this type of soil has different applications. First of all, you must have studied that here you have a flocculated structure. The grains are flocculated. But here, this is the dry of optimum, and this is the wet of optimum. Here you have a dispersed structure of the soil because it has come together, isn't it? Now, no doubt the density is same, but the structure is no longer flocculate. Second thing is about permeability. If you see, permeability of this structure should be greater than this structure. If you have, because it has the volume of the voids is not the total volume, but the shape of the voids is more conducive of water transport. So we have a high permeability here. We have a low permeability here. And other thing, let me check what are the other things that we want to discuss. Wet of optimum and dry of optimum. More or less, this is the idea. So let us move on to our questions. If you have any question about compaction, you can always contact me on my email, which I mentioned in previous class also, s underscore SYED at the rate CE dot IITR at dot AC dot in. Okay, so let's move on to our first question for the day. The laboratory test results of a standard Proctor test are given in the following table. Volume of the mold is given, the weight of the moist soil in the mold is given, and the moisture content is given. Determine the maximum dry unit weight of compaction and optimum moisture content. Also calculate and plot the gamma D versus moisture content for degree of saturation equal to 80, 90, and 100. This is ZAV. And given that GS is 2.7. Okay, so first of all, first thing you need to know is what is a compaction test, that I am very sure that you are already aware of. But if I tell you if I reiterate the procedure of compaction test, then you will understand this question, why is it modeled in this fashion. Okay, so in the lab, what we do is we take this mold. It's now not about reading from a book or anything, just the practical experience. You get the mold, and you get some soil in a dry state, most probably, and you add about 10%, 8% of water, 8% of water to this soil, such that because this is dry, such that it comes at a water content of 8%. Now, the water content is not exactly 8% because of the error we might, the human error, like when we are mixing this, but around this it will be. And then we fill this, damp this for 25 blows of a standard hammer, which you already know, 25 blows in three layers. And then we open the mold, not open, open the collar, and then we weigh this mold. We know an empty weight, and then we know a fill mold weight. We know the volume of the mold. So what we know from this data is the total bulk density of soil, isn't it? Because we know the volume. Volume is standard 1000 cc, and the weight, what we do is the filled weight minus empty weight. We will know the weight of the soil inside, and bulk density is weight over volume. So we know gamma B. Then we disassemble this sample and we try to take a sample from here, from here, from here, and we put it in the oven and we check the moisture content by oven drying method. Then we can be sure how much is the moisture content. And after that, after this first trial, what we do is we add 2% more water. Then we do the same thing. So we will know a gamma B1, gamma B2 at about 8%, 10%, 12%, 14%. So this is how we perform this test. And how do we know when the test is almost like when the test should be terminated? See what will happen in sandy soil, in coarse, fine grained soils. What you will have is uh, you will have this compaction curve. You see, as the water content is increasing, the density will increase, and at this, after this, the density will decrease. Because the volume is constant, we can say that the weight of the mold will initially increase as water is increased. We want almost at least readings here, two readings here. So when we see that our weight is decreasing, you see here weight is increasing, increasing, now it's decreasing. Then we want two readings after that. So this is what we keep in mind, that uh, as soon as the weight starts decreasing, then we take two more readings and then we conclude our test. Then from the W, the water content and the bulk density, we calculate the dry density. And then let us do that for this question. And just like the first lecture, in this lecture also, we will be uh, doing some of the questions in Excel. So let me open an Excel file. Okay, so let's first copy this table to this file. This we don't need to copy, we already know how much that is. We just need these two columns. Okay, so this is the question one. So we know the volume of mold is 1000 cc. So from the weight, we can calculate the bulk density by dividing the weight by volume is equivalent to weight over volume. I want to log this because volume is constant and we don't want Excel to change it during the formula. And then we can drag this. So these are the bulk densities of the soil during the testing. Then we calculate the dry density. You know the formula for dry density. The relation between bulk density and dry density is gamma D equals gamma B over 1 plus W. So let's use this equation here. Gamma D equals gamma B over 1 plus W by 100 because this is in percentage. Okay. And this is in gram per cc. This is also in gram per cc. Let me get rid of the extra. Okay. So this is the moisture content and this is the dry density. Now let us plot the moisture content versus dry density. Okay. Let us insert a chart. On the x-axis, we will have the moisture content. On the y-axis, we will have the dry density. And the series name, let's say compaction curve. Okay, okay. Let us do some editing so that we can see this properly. This is 1.46 to 1.66. Major is 0.1 maybe. That's too much. 0.05. Yeah, that's better. And okay, let's start this from 5%. Okay. Mm, it's one and the same thing. It will not matter, but it's because it does not matter from where it is starting. Okay. So this is our compaction curve. Let's try to calculate the OMC and the MDD. Use a dashed line somewhere here, isn't it? If we see the data labels, our OMC is 1.65 at what I can do is I can include minor, yeah, so this is 14%. So our MDD maximum dye density is 1.65, which is at water content. Oh, it was there only. 1.65 was here. Okay, at 14 uh, percent of water content. So the first part of our question has been determine the, this is the A part, maximum unit weight of compaction and optimum moisture content that we have done. Calculate and plot the gamma D versus the moisture content for degree of saturation 80, 90 and 100 given GS is 2.7. Okay, now let us try to do that. We know gamma, we know the formula for gamma D equals G gamma W over 1 plus E, isn't it? And GW is equal to ES. We know G, we know W, we know S, and we can take E from here is equivalent to GW over S. So we take gamma D equals G gamma W over 1 plus GW over S. Okay, so let's draw this table here. GS has been given 2.7. Water content, oh sorry, water content has been given here. So the water content has been given, and now we want to calculate for S is equivalent to 80, S is equivalent to 90, and S is equivalent to 100. Okay, so from this formula, G gamma W 1 plus G W over S. So G, let me write from the formula here, G into gamma W over 1 plus G into W over S. Okay, and gamma W is 1 gram per cc because we are talking in gram per cc form. So GW is 1 gram per cc. If it was in kilonewton per meter cube, you would have taken 1000. Here, this is equivalent to G. Let's lock this because we don't want this to change into this. Maybe I will change the units, so I will not take it as lightly. G gamma W over 1 plus G, let's log this, into W over, I should have written S here. Okay, it's going to give me an error because I've written S is equivalent to 80. So let me correct this. Let me write S here, and let me write 80. This should be fine now. 90 and 100. And from this formula I need to fix this. G gamma W 1 plus G W over S. Okay, so okay. Let me write 0.8. This is 0.8. No, this is fine because water content is also in percentage, so it will cancel out. Okay, let me bring it here. So these are the values of gamma D for 80% of saturation. Let's do these for 90 and 100%. I just need to change this and this. And for this, I need to change this and this. Okay, so these are the values of water content of sorry gamma D at, this is gamma D at S is equal to 80, 90 and 100%. Okay, let's try to plot these on this graph. Let's say S equals 80. X value is water content. Y value is this. What happened? Okay. Add S equal 80. X value, water content, Y value, this. X value, water content. This is giving me a hard time. X value, water content, and Y value is this. Okay. Now let's add S90. The X value will be this. The Y value will be this. Okay. Now let's add the zero air void line. Let's call it ZAV, where our saturation is 100%. X value is this. Y value is this. Okay. Okay. Something. Let me fix this. Reset. Okay. Let us actually start at 1. Okay. Or 1.2. So this was our OMC and MDD. So the question was asking, calculate and plot gamma D versus the moisture content for degree of saturation of 80, 90 and 100%, given G of S is 2.7, and that is what we have done. This is what we have done. Okay, let's say okay. Excuse me. That is our first question. So let's move on to the next question. Let's move on to the next question, to the second question. A modified Proctor compaction test was carried out on a clayey sand in a cylindrical mold that has a volume of 944 cc. The specific gravity of the soil grains is 2.68. Moisture content and the mass of the six compacted specimen are given below. So we have been given again the mass of the specimen, excuse me, and the water content, and what we need to determine is the what we need to determine plot the zero air void curve and check whether it intersects with the compaction curve. So first we need to draw the compaction curve for this. Let's do that. So this is our question 2. Let us write here mass 1776 1890 2006 2024 2005 and 1977. And here we have the water content, which is 5, 7, 9.5, 11.8, 14.1 and 17. Okay, so volume of mold is 944 cc. Okay, and the GS is given as 2.68. Zero air void line, void ratio, and the degree of saturation against moisture content. Okay, let's first try to do this. So from the mass, what we will calculate? The bulk density. Bulk density will be mass. This is in grams. Let me write in grams. And this is in percentage. So from the mass, we will get the bulk density, which is this over volume. Let's fix this. Okay, and this will be our bulk density. And now from bulk density and water content, we will get dry density in gram per cc. This is equivalent to bulk density over 1 plus water content, but not in percentage. So this is just your formula of dry density is equivalent to bulk density over 1 plus water content. And from here we calculated the dry density. let's calculate for all of the values. Okay, so this is our dry density, and now we will uh, draw the compaction curve between the dry density and the water content in x-axis. Insert a chart, select data, add series name, compaction curve. X value is W, Y value is dry density. Okay, so this is our curve, compaction curve. Let's start this from, let's take major as 5 and take this from 0 to 20. Okay, and let's take on this axis major as 0.5, and let's take this from 1.7 to 1.95. 0.05. Okay, 1776, 1890, 2006, 2024, 2005, 1977. Okay, so let's calculate the MDD and the OMC. Actually, let me take this. Somewhere over here. So the OMC is almost 10%, and the MDD, let us draw the minor tick lines so that we can see better. Tick marks, minor, inside. Okay, now color of tick marks, black. Can we see? It's almost 1.9123, 1.94. Okay, so we will have an OMC of 10 and MDD of 1.94 gram per cc. Okay, So from this, let's move on to the next part of the question. Plot the zero air void curve and check whether it intersects the compaction curve. So zero air void is full saturation. Now we have been given, just like in previous question, what we will do, we will take S equal ZAV में S is 100, so we will take gamma ZAV, zero air void, let's say density. Okay, this will be GS into, one second, let me write gamma W here as 1, and let me show you again what I'm using. I'm using this equation G gamma W 1 plus GW over S. So I will have G into gamma W over 1 plus G into W over S is 100 for ZAB line. Okay, and it's asking us to plot this line and show that the zero air void line does not intersect the compaction line. So we add this line, let's call it ZAV. X-axis is the water content, y-axis is the density at ZAV. Okay, okay. So I need to change the limits here. This is okay. So this is the ZAV line. This should be at least 0.1. Okay, 0.2. So this is the zero air void line, and as you can see, it does not intersect the compaction curve because in actuality you cannot have zero air voids. Okay, so we can see all the plots. Let me change the chart design. So all the values from the test, they lie to the left and below the zero air void line. So it's the next part. Calculate and plot the gamma D versus moisture content. Okay, this is the previous question. Plot the void ratio and the degree of saturation against the moisture content. So let's calculate the void ratio first. Okay, we know that GW equals ES. We know the G, we know the W, and we want to calculate E and S. So what we will do is first we will fix the, let me check, is this at ZAB? Okay, so from here what we will do is we will back calculate the way we calculated the ZAB here. We calculated the theoretical density. Now let us keep this as the experimental density values that we have, and what we will do is we will use this formula, gamma D equals G gamma W by 1 plus E. Let me write it here. Gamma D equals G gamma W over 1 plus E. That implies 1 plus E equals G gamma W over gamma D, and E equals G gamma W over gamma D minus 1. From this we will calculate E, and then S we will calculate as GW over E. Okay, so let's do that. G gamma W over gamma D minus 1. Void ratio is G gamma W over dry density minus 1. So this is the void ratio, and saturation we will calculate as, this is equivalent to G into W over E. Yes. is in percentage, or we can take W in uh, not in percent form. So this will be our degree of saturation. It's better to take in the no, this is fine. So now they are asking us next question. The question is asking us to plot the void ratio and degree against the moisture. So okay, we will draw another plot. Void ratio, X will be our water content and Y will be our void ratio. Okay, okay, okay. Now let me do one thing. Let me plot the degree of saturation. Okay, okay. And let me do this on a different axis. So this is the axis for void ratio. Let me add axis titles. This is void ratio and this is degree of saturation. Okay, and this is water content. We can start this from 0.2. Okay, and then we have this. We can start this from 0.3. Okay. Hmm. We don't need a chart title. So this will be our variation of void ratio with degree of saturation. But for better comparison, let us do one thing. Let us plot both on equal y-axis, 0 to 1 and 0 to 1. So, oh, 2. Okay. So as you see, as water content increases, the void ratio first decreases and then increases. And as degree of saturation, as water content increases, degree of saturation just increases, which is what our compaction actually says. See, as water content increase, obviously the saturation will increase. But about the density, as we could see that the density would first increase then decrease. That means as density is increasing, void ratio is decreasing, and as density is decreasing, void ratio is increasing. If I plot this on this, I should have 1 second. Let me do that actually. Let me plot this on secondary axis, and then I should add a plot, add gamma d dry density. So the x value will be same, but the y value will be the dry density. Okay. 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 So this I am plotting on the primary axis, which is starting. 1 second, just a moment. Uh, Excuse me. So, okay, we were talking about this. So now this is dry density, and this should be on secondary axis. This should be on secondary axis. Let me add axis titles. Secondary vertical. This is E or S. This can start from 1, 0.6 to 2. 1.5 to 2. 1.8 to 2. can be 0.05, 0.05. Okay, so as you can see from here, as the density is increasing, the void ratio is decreasing, and just as the density starts to decrease, the void ratio starts to increase. So that is what I wanted to show you. Okay, okay. So, okay. Oh, excuse me. So let's move on to the next part of the question. What are the void ratio and degree of saturation at the OMC? And you know the OMC is almost 10. So the void ratio and the degree of saturation will be uh, here. The degree of saturation will be 70%, and the void ratio will be almost, this is 0.39. So the degree of saturation, as we could see, this was E came out to be 0.39, S came out to be 0.7, and OMC and MTD came out to be 10 and 1.94. Okay, so let's move on to the next question. The maximum and the minimum unit weights of a sand collected from the field were determined in the laboratory as 18.38 and 15.99 respectively. It is required that the sand in the field be compacted to a relative density of 85%. Determine what would be the relative compaction in the field. So, as we had discussed that why we do this compaction test is that we want to translate these properties OMC and MDD to the field. Now, in last lecture also I mentioned that as soon as that you take the soil out of the ground and the sample becomes disturbed, now the density of this soil will not have any significance in any kind of procedure because now it is different than what is in the soil. But for sands, we have a vibration vibratory table test, in which what we do is we take a mold and first loosely place soil in it and then calculate the density, which is the maximum minimum density or the maximum air void, and then we shake this table until the particles settle and they get arranged in a very uh, as compact as possible manner. So then we calculate the gamma D, which is the maximum density, and then we calculate the gamma E minimum. So the maximum and the minimum unit weights of sand have been given. Gamma max is 18.38 kilonewton per meter cube and gamma D minimum is 15.99 kilonewton per meter cube, respectively. It is required that the sand in the field be compacted to a relative density of 85%. So the relative density is the field density minus gamma D minimum over gamma D maximum minus gamma D minimum. This will be relative density has been given as 85%, that is 0.85, equals gamma field, which we want to calculate, minus 15.99 over 18.38 minus 15.99. Let's calculate this. Oh, there's a correction. Sorry. Actually, that was E maximum and E minimum, this formula. And when we translate it to gamma, we write 1 by gamma minus 1 by gamma maximum divided by 1 by gamma minimum, 1 by gamma maximum. Okay, so gamma minimum, gamma maximum minus gamma D divided by gamma. Okay, this should be gamma minimum. So this will be gamma minimum minus gamma. Okay, now we can calculate 0.85 equals 1 by 15.99 minus 1 by gamma over 1 by 15.99 minus 1 by 18.38. Okay, so let's calculate. So this will be gamma minus 15.99 over gamma into 15.99 into 15.99 into 18.38 over 18.38 minus 15.99. This and this will go, and we will have gamma minus 15.99 over 18.3 18.38 minus 15.99. 2.39 into 18.38. This is 0.85. This will be 2.31 into 0.85 over 18.38. 0.11 equals gamma minus 15.99. So gamma equals, this should be plus 15.99, 16.1. So the gamma field is 16.1. So now we want to calculate the relative compaction. Okay, the relative compaction is gamma d field over gamma d max minus, no, gamma d max, which we have determined in lab, into 100. So gamma d field we already know 16.1, and gamma d max is 18.38 into 100. This will be 16.1 over 18.38 into 100. The relative density will be 87.6%. Means that it is 87.6% of the maximum density it can achieve. In totality, it is only 86 87% of the maximum density it can achieve. Relative density. Gamma d field over gamma d maximum lab into 100. That is what we did. I think there is a mistake while calculating the field density. Okay, let's calculate the field density again. We know that RD. Okay. I misread the question. No, this is fine. Let me write this without the denominator, everything. This is gamma D minus gamma D minimum over gamma D max minus gamma D minimum into gamma D max. This is essentially what we did actually, but there is a calculation error as far as I think. Gamma D field. So RD is 0.85. Let's try to calculate now. Let's write it like this. Gamma df equals gamma d minus gamma d minimum, gamma d max, gamma d minimum, gamma d max, RD. Okay, let's solve this portion. Gamma d maximum is 18.38 minus 15.99. This is 2.39 into relative density is 0.85. Okay, 315 and 18.38 is divided by 2.0315. So this is gamma df equals gamma df minus 15.99 multiplied by 9.05. So 15.99 into 9.0. Actually, I should have done what I should have done was take an inverse of this. 0.11 gamma df is equivalent to gamma df 0.11 minus 15.99. Okay, I got it. Where I did the mistake. Gamma df. I just added 0.11 and that is not what I was supposed to do. Okay, is equivalent to 15.99 over 1 minus 0.11. 0.89, 15.99 divided by 0.89. Okay, so it comes out to be 17.97 gamma D, gamma field. Okay, so here we take this as 17.97 and this comes out to be not 87% but 17.97 over 18.28 into 100, 97.7%. So our relative compaction is 97.7%. So it is 97.7% compacted. Okay. So that was, these were our questions on our field compaction. How much time do we have? Yeah, we have some time. We can do another question. Okay. For a given soil, GS is 2.72. Following are the results of compaction test conducted at the laboratory. These are the tests from the lab. After compaction of soil in the field, sand cone tests were conducted at separate locations. Sand cone tests are conducted to determine in situ density. Okay, so what they are saying is that first we did the compaction, then to check for degree, like then to check for how much compaction has been achieved, we did in situ density tests, sand cone tests at different locations, 5 different locations, and from there we wanted to see if our relative density or relative compaction is high enough or not. Specifications require that gamma D must be at least 95% of gamma D maximum. First thing is that our gamma D in field should be at least 95% of gamma D maximum. So first we need to draw the Proctor chart and calculate the gamma D. Second specification requires that moisture content should be within 62% of W optimum. We know the moisture content from here. We will calculate the W optimum and check if this is, all these are within 62% of the water content or not. Okay, so let us take this to Excel and try to find OMC, and the MDD. 1 minute. 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 1 This is question number 4. Okay, and we have the dry unit weight directly, moisture content and dry unit weight directly. So we don't need to calculate from weight and everything. We just have the entire data. We just need to plot. Let's do that first. We are inserting a plot. On the x-axis, we will have the moisture content data. On the y-axis, we will have the dry density. Okay. Okay. First of all, let me 16 to 17.5. Okay. We don't need the chart title. Let me include the axis titles. This is the dry density and this is the water content. This is the first part. Second thing, okay, first we need to calculate the OMC and MDD. Sorry, I forgot. Somewhere here, okay, somewhere here. So this will be about 17 and this will be about minor will be 1 tick marks minor, minor will be zero point 0.1 tick marks minor. Let them make some, let's make them a little visible. Okay, so almost here. Okay, so this is 17 and this is 16.5, 17, 17.1, 2, 17.25. MDD is 7. Oh, so our OMC is 17 and our MDD is 17.25. Okay, So let's move on to the next part of the question. Okay. After compaction of the soil, field sand cone tests were conducted at 5 separate locations with the following results. Okay. Am I missing something? Okay. So 2.72 has been given as GS. Let's do one thing. Let us draw the ZAV line. ZAV line S will be 100, and we can ZAV density will be, this will be G gamma W. Let me write gamma W here, over 1 plus G W over S. Gamma W was 1. Okay, gamma W has to be, excuse me. Okay, gamma W has to be locked in. Okay, so let's draw this ZAV line here. X value will be this, Y value will be this. Okay, okay. Okay. Because this is in kilonewton per meter cube, I cannot take 1. I have to take 1000. Okay. Not 1000, 10. Sorry. I have to take it 10 kilonewton per meter cube weight of water. So this is a zero avoid line. Let's start density at 15. Okay. This is the ZAB line and this is our compaction curve. Now let us do one thing. Let's take these points from different locations. So these are the moisture content and moist density of uh, the sand replacement method that was done, but this is in kg per meter cube. So this has to be converted into kilonewton per meter square. Because I have taken already 10, so I will not take 9.81. Let me convert it using G is equal to 10 only. Okay, okay. So this is the moist density, and the dry density will be this over 1 1 plus this over 100. This is the dry density. Okay, let's draw these as scatter points. Okay, location 1, x value is this, y value is this. Okay, One second. Uh, Edit. I will take this column. I'll take this column. Okay. 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 And I will start it first. Okay. This is fine now. And let's make it a little more visible. Give it a better color. Okay. Okay. So now, what is the requirement that the question is talking about? Question is talking about gamma d must be at least 0.95 times gamma d max. We already calculated the gamma d max. MDD now 0.95, 0.95 of this is 16 point this thing. So if I take a line at 16.38, something wrong with the monitor, just a moment. 16.38 is almost 16.4. So I will insert a line uh, at 16.1, 2, 3, 4, 5, 16.2, 16.4. So technically, no density should be below this. Okay, no density should be below 16.4. 16.4 is here. So basically, no density is actually below this. But moisture content should be within 62% of W optimum. W optimum is 17%. And 62% of this is 10.54, which means, um, just a moment, my screen is glitching a bit. Within, it's not 62%, this is 2%. I'm sorry. It should be within 2% of this. I will multiply this by 2. So it means that plus 3.4, 17 plus 3.4, 17 minus 3.4. That is 20.4 and 17 minus 3.4. 13.6, 17 plus 3.4. 20.4 and 13.6. Okay. So let me draw these lines again. This is 13.6. Almost here. And 20.6. 20.4. Somewhere here. Okay. So the requirement is that the moisture content should be within this, which we can see for these points, and the dry density should be below this, within above this, which we can see. But if you see here properly, there is a location, which is location 5, in which our point is even above the ZAB, which is not possible. So we can say that this uh, uh, calculation or determination of this point must be erroneous. This has some kind of a problem with it. Okay, so these are location from locations 1 and 2, and these 2 points meet our specifications. Okay, sorry, these are points 1 and 2, and these meet our specifications. Let me check. There's an error somewhere. Let me take this as 9.81. Okay, then I would take this as 98.1. Okay, so yes, 2 over 1 plus W by 100. Let me not change it here, lest it will bring some kind of error. Let me change it here into 9.81 over 100. 1000. Hmm. So there was a error, recurring error that was because of like the 9.81 thing, and it was getting carried on. So that is why we're not getting the correct results. So this is a borderline case 3 because it is almost on the 95% density, but 4.4 is below the 95% density. So we can say these points are okay, but this point itself is erroneous and this point does not meet the specifications. Okay, so these were the questions on compaction that I had planned to discuss today. And again, if you have some question, if you have any question, you can contact me on my email. And I think that is that for today. Thank you very much. Have a nice day.